the topic is breakthrough propulsion. What is breakthrough propulsion? Yeah, so you know liquid propulsion, electric propulsion. What is it? Breakthrough propulsion? Well, breakthrough propulsion is science fiction, basically, right? So how to go to the stars. When I grew up, I saw as a kid, I saw Star Trek on television, said, cool, yeah? So you push the button, it's a warp drive, and in some minutes or hours or whatever, we go to other stars and we meet other civilizations or whatever. That would be super cool to do something like that, right? And then, you know, I studied and realized that's very far out there. And basically, it's impossible. Yeah? So is it only going to be science fiction? Or is it just us, and we need to be a little bit smarter, yeah, to actually realize our dreams? Here in the movie Interstellar, there was a black hole in our solar system. Good for us. That's not the case, okay? Otherwise, I would not be here. And so the warp drive, this is, I mean, they could have named it X or whatever, yeah, a different name. Just this magic machine that does the job. This is something, of course, that we would all very much enjoy if we come across this kind of technology. So actually, I mean, Interstellar Symposium, you're all aware of this, but a little recap. What's actually prohibiting us from achieving this dream? There are three limits. First of all, the distance is pretty far away. Second, we want to achieve it in a certain amount of time. Obviously, this is limited by the speed of light. Yeah, as I have it here. And then we also want to achieve it with some mass or payload actually to arrive there. So those are our three fundamental limits. And the interesting part here is that actually right now we can do 2 out of 3 in whatever combination you choose. You could do 2 out of 3, but just all the 3 together, that's the really hard part. Yeah? So let's briefly have a look at what I mean here. So for example, the distance, what are we talking about? Well, if we talk interstellar, should be at least the next star, right? No clue if this is really of interest to us. So there are some exoplanets, but if there's life, whatever, no one knows. But at least it's our neighbor, and we have to show up, right, and say, here we are. So that's the minimum distance, right? It would be fun to go to something like the TRAPPIST-1 system, that there are several planets probably in a habitable zone. Why have we not been born on such a star system to hop from one habitable planet to the other one? That would have been really super cool. But, well, that's 40 light years away. Okay, but at least 4 light years we should do. The time. Well, I applied to a project and want to realize something. And so what about we realize this in a typical project duration, let's say 4 years, yeah, PhD, whatever. We want to build a warp drive 4 years. Yeah? So that's one approach. The other one is let's at least try to achieve this within a human kind of life cycle. So you drop out of university, I grab you by the hand and I say, look, I promise to you, yeah, you step inside this machine, yeah, and in 50 years you get prime time all around the world, okay, I promise. Yeah? So if you find such people, that would be great. And 50 years in the can and, you know, off you go. Or the other approach is just as long as it takes. Yeah, so that's another approach to take on time. And what about mass and energy? Well, minimum is I have to get there, right, with 0. Then at least I would like to have some sensors, right, to take a picture or whatever. Or what about going with something like the Space Shuttle, Starship or whatever? That's what I've been dreaming about, right? So those are our 3 limits. And as I said, pick 2 of them and we can do it. Yeah? So for instance, let's pick the distance and mass. So we want to go to the next star and we want to go there with some mass. Well, that's, for example, the Voyager probe. So just takes 10,000 years to go there. Yeah? We will not be alive, but so what? Time is not the issue here, but distance and mass, we can do it. It was launched, and it's really, I mean, this is for the history books, right? We left the solar system, kind of, yeah? So that's really, that's a humankind moment. And it just takes a lot of time. And I mean, we even we have a present with this probe, right? So it's our habit. You go somewhere first time, and you have a little gift, right? So we have nowadays we would send maybe a USB stick with some MP3s. At this time we have the golden long playing record, and so when the aliens will actually try to play this. they will listen to an Austrian speaking English, like myself, because Kurt Waldheim was the Director General of the United Nations at that time, so they will all think they talk like me. Anyway, yeah, so this is one example, so that's doable. What about another example? What if we do the distance and the time? Yeah? So distance and time, but let's say with zero mass. Yeah? That's possible too. So you heard my student talking about aerographite solar sails. We are trying to get our hands dirty on that one. So here, for example, we have aerographite sample, and we shoot a laser beam and trying to measure really what's the force, the photon thrust force on this aerographite sample. And if you can make it really very, very thin and of sufficient size, and you go like the Parker Solar Probe close to the sun and you release it, then there's a chance that you can go then something like 100 years. Yeah? So it's not our 50 years, but let's say around about 100 years, you go there, and actually we just send a smoke signal. So, and maybe, I mean, that was the first kind of communication from us anyway, right? We send smoke signals from maybe one hill to the other one, so we can also send a smoke signal to the next star, and let's see what's happening. Yeah? So maybe Morse code type or whatever, who knows? So that will be fun. And by the way, I'm a huge fan of doing something for real, not only spending my time with the pencil on the paper, yeah? Because you never know, there's always something unexpected, yeah, when you do it for real. There are some surprises. For example, some people said, oh, why do you want to measure, the light interaction with this aerographite material? It's pitch black, so it will absorb. I can just calculate what's the thrust force, right? Why do you need to test it? Well, we put it to the test. First test, we measured something much bigger than the photon pressure. So what the hell? Is something wrong with our laser? Something wrong with our thrust balance? No. We also realized that there was a peak in the pressure in our vacuum chamber, because this material is such a super sponge that it keeps air trapped inside, even in high vacuum. So we shoot with our laser on this material, and it produces, of course, hot gas being expelled on the other side. So that's a very nice additional thrust benefit, totally unexpected. So actually, we can probably make it in less than 100 years if we take this thrust effect into account. So you have to do things for real. Well, what about doing all these three limits? Yeah? So what about if we go distance, time, and just a tiny mass? Yeah? Well, that's Breakthrough Starshot. I don't have to tell much more about this here in the audience, but it's still a super challenge. I mean, numbers are something like 100 gigawatts on your light sail for a couple of minutes and so on. So that's really super challenging, and also, where do you get 100 gigawatts for a couple of minutes? Just the power requirement here is really absolutely enormous. So people are trying to shake this a little bit, but most people probably will still think that this is really, if it's possible, it's really far away. And now let's take everything together. Let's build our dream machine. Let's say, okay, let's take the space shuttle. I mean, that's at least a starship that I can imagine. Let's take something like the space shuttle. Let's bring, an astronaut in there, and let's say, okay, you go to the very next star, and you do this in 50 years one way. And we take the space shuttle because I checked for 50 years, I mean, this person needs to be alive, so we need to feed him. And some of us fondly remember our days as students. And so I checked ravioli in these cans, cans and soups and this typical student food. Well, 50 years of student food, it's about half the size of the cargo bay of the space shuttle. So we can stuff in the student food, the rest is air, a couple of books, yeah, and that's it, yeah. So he can make it, and we will give him the best propulsion system that we've ever conceived, yeah. Ray of light, that's great, yeah. Electric propulsion, super, but come on, let's do this to the extreme. What about just taking a small, tiny nuclear bomb drop it behind our spacecraft and push the button. So we all agree it cannot get better than that, right? So this is EMC square, boom, yeah? Plus I don't have to worry about my propulsion system because I have to send a new bomb. So it's, I don't have to worry about lifetime issues and so on. I just have to worry about my spacecraft, but the propulsion system will work. And it's off-the-shelf technology, and it would be fantastic to just use all these nukes and use it for something good to go maybe to the next star. How many of these nukes do I need? By the way, we are talking about very small nuclear weapons, obviously, because, I mean, it's really funny. You can even check this on Wikipedia. When you have a small nuclear bomb, maybe 20-kilogram class, and you push the button, there's a so-called fireball radius where everything is just vaporized. It's just 10 meters. So when I drop it behind my spacecraft and, 10 meters far away, push the button, if I have a shield of tungsten, I can survive. And I get 1/6 of the blast of this nuclear weapon to propel my spacecraft. That's as good as it gets in terms of thrust, specific impulse, just everything, okay? How many nuclear bombs do I need to propel a space shuttle in 50 years one way to just the next star? It's the mass of the sun. Okay, so that means, okay, crunch some more numbers, yeah, that's not going to make it, right? Exactly, that means, my God, this is really what I call impossible. We need a breakthrough. We have to do it different, yeah? Not F equal to N times A, no Newton's mechanics, no Albert Einstein theory, whatever. We have to reinvent the wheel. We have to do it somewhat differently. It will not be possible with energy and propellant. Nevertheless, there's some good news coming. We have no clue how the universe works. There's so much things that we don't know. Good for us. So the trick could be out there. We have just not seen it or didn't stumble across it. When I was a kid, I was being told, look up, what you see, that's the universe. Now I'm being told that when you look up and you see all these stars, oh, that's just 4% of the universe. The rest is dark energy, dark matter. This is kind of a placeholder for something that we just don't know. We have no clue what it is. We just know it must be there because otherwise our measurements don't make any sense. But what's the real reason behind that is the best answer is actually we don't know. Yeah? So dark energy, it seems like, I mean, this is the dominating factor in our universe. It seems like someone is kind of, pumping space-time inside our universe all the time, and it keeps expanding and expanding. Our universe gets larger and larger all the time, so kind of cosmic anti-gravity happening on a large scale. That's great, yeah? If I would know what this magic force is, maybe I can do something with it, yeah? And what about dark matter? Actually, it's supposed that there is much more dark matter out there than the usual visible mass in the universe. What is it? We can just kind of indirectly know that it's there because, for example, if we look at galaxy rotation curves, if I go a little bit farther out, if I have here the center, I go farther out, I know from the luminosity what's the mass of the stars that should be there. I do some numerical modeling, and so I will realize that if I go out there, I should actually see a decrease in the velocity. But in fact, I see that nope, actually the velocity stays the same. So either the two options, either there's much more mass there that I just don't see, that's why I call it dark, or Newton's mechanics don't apply on that scale. That's a possibility too. That's called MOND, modified Newtonian dynamics. Both are maybe possible, and we look for propellant out there. Maybe it's dark matter. That's apparently everywhere, yeah? And it's actually much more than normal. So we just haven't found any way to connect to dark matter. We say it just acts gravitationally. I cannot touch and feel it, but if I could make maybe a dark matter propeller. Yeah? Then I don't have to worry about the rocket equation. I don't have to carry propellant with me. It's there everywhere. So I can just make a propeller with, being propelled by, for example, a dark matter. But let me introduce you maybe the most fundamental idea of how to achieve maybe the ultimate propulsion principle. Something very, very simple to imagine. Just for you to know that it could be possible if we just find one magic trick. We are just one magic trick far away from doing the impossible, okay? So let's imagine something that we can all imagine very well. Let's say football, okay? So if you see somebody running towards this football and you hit it, then chances are very high that you will see that the football is actually, traveling the same direction as you hit it, right? That's everyday experience. Now I'm coming up with a magic trick. I'm playing David Copperfield. I'm inventing a negative football. Yeah? So what if this football has a negative mass? And I try to hit it. What's happening? It's actually coming to me. Nothing really forbids me of doing so. F is m times a. Newton didn't say it has to be the absolute value of mass. Maybe he forgot, whatever. But it's possible. You can say F is minus m times a. It could be possible. And then you can make, if you give me minus 1 kilogram, I can build a warp drive right away. Yeah? Because I just have to take my positive football and the negative football next to each other. Let's say I charge them up such that the positive is attracted to the negative is attracted to the positive. What's happening? So the positive one, it's being attracted to the negative one, so it moves to the right. The negative is attracted to the positive one, but it moves in the opposite side, so they both start to move in the same direction. It's a self-accelerating system. That sounds cool, huh? So some physicists will say, oh, that's forbidden, okay, yeah. You are violating the principle of energy equivalence and momentum, blah, 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 blah. No. mv square half, that's kinetic energy of the plus football, and minus mv square half is the energy of the negative football. Together they are zero. This is just the natural system, that's the natural ground state of this self-accelerating system. So that sounds fantastic. That looks like our imagination. It's just someone has to invent minus 1 kilogram. That's the magic trick that we're talking about. So where could we find this magic trick? Maybe some people say, oh, I've heard about this, yeah? Maybe this relates to, the Casimir effect, yeah? So for example, who says that here, basically if we remove everything and we're in vacuum, who says that this is really zero? Zero is where we define zero to be, right? So this is our reference. We say it's zero, yeah? Because we don't see anything else. We define the vacuum kind of as zero, but it could be that the vacuum is actually not zero, but we're standing on a huge mountain, but we just don't realize. If you are born on the top of a mountain, it's very flat, just move around a little, you probably will believe that you are living on the floor. Yeah? Just when you start to dig a hole or when you approach to a cliff, you actually see that, oh my God, I'm actually far above, right? So it could be that the vacuum is full of energy and we don't know. So this is to dig something into the vacuum that has been done. This is called, for example, the Casimir effect. And if you have two metallic plates and you move them very close to each other, you will see that they are actually pushing together. Yeah? So, okay, so that means that the vacuum can have a negative state with respect to me, so I can make negative energy, negative mass, but how much can we do? I crunched some numbers, okay? I said, okay, what's the smallest distance I can do? What's the smallest positive mass that I need for that? Let's say a carbon nanotube. Carbon nanotube, so that's a single sheet of atoms, yeah, wrapped, one wrap, very small wrap. You can calculate what's the negative energy inside this carbon nanotube, so that represents EMC squared to a negative mass. How much negative mass do I have inside my carbon nanotube? Carbon nanotube is also very lightweight, and the negative mass is something like 20 orders of magnitude below the positive mass. So, bah! Unfortunately, no. Some people thought maybe it's antimatter. This is something that's being produced in CERN, for instance. That is, they smash particles together and they make antimatter. Antimatter is something magic. According to Richard Feynman, you can describe antimatter as particles actually they go backwards in time. For example, if you have an electron and the electron is being attracted by a positive charge, so it moves there, and you have a movie, you make a movie about this process, and you see how the electron is being attracted to the positive charge. Then you look at this movie and you run it backwards. Then you will see, oh, the electron now all of a sudden is repelled actually from the positive charge, as if it would have a different charge. So we call this a positron. It's just the electron flipped. So you can say, okay, it has a different charge. The magnetic momentum is the other way around. Hey, who says when I drop the electron, it's attracted by the Earth. What if I rewind, my movie machine, maybe the electron is actually flying upwards, the antimatter electron, so a positron probably would repel from the Earth's gravity. This would be something like negative mass. Actually, this has been very recently tested, just a couple of months ago. People were long dreaming about this, yeah? So most physicists said, nothing unusual will happen, yeah? But nevertheless, you have to check. And for that, they had to make neutral antimatter. So if you have charged matter, it's very difficult actually to see gravity because electromagnetism is so dominant. Yeah? There are always some rest charges somewhere. So you have to make a neutral atom. Yeah? And so they made anti-helium. Yeah? And with anti-helium, they just get 100 anti-helium atoms, yeah, at least, but they could check if there's some sedimentation between helium and anti-helium, and they found no. It behaves the same way gravitationally as the normal helium, so unfortunately, no negative mass here. Nevertheless, I have an opinion about this. You can ask me in the question and answering session afterwards, yeah? So, yeah, I already said to you, another idea is to hope and pray that maybe if we advance our knowledge in dark energy and dark matter, that we will find some answers that we can use for propulsion systems. So like this dark matter propeller, or we find some ways to engineer the vacuum. Maybe this is the science of the 22nd century, yeah? So that we engineer the vacuum to our needs and to find some ways of how to use vacuum as a medium to do propulsion. So yes, breakthrough propulsion is something that I really try always to do, to try to push the limits and push the envelope. I have a web page, probably that you want to check out, where I have all the papers that I did in all these years to look at that. So from the theory to testing claims from other people that believe they found a breakthrough. EM drive, you can ask me in the Q&A on that. Mass modification, looking for new forces, something like this. So I've trying to do this kind of all my life. As a teenager in my children's room, I had a 100 kilovolt power supply with 1 kilowatt of power, half a ton of high voltage capacitors. I love electricity and high voltage. So I tried to fool around so long story. And because I don't have too much time, I will just pick something that I think is very appealing and very educational, and also something that kicked me off. Yeah. So as I said to you, I really like electricity because electricity, that's kind of our modern society. Without electricity, everything is literally dark. Yeah. So with electricity, this is driving. We can control electricity. We can make high currents, high voltages, high frequencies. We can transform it. We can store it. Yeah. So electricity would be fantastic. So if there is any way we can achieve this warp drive or play with gravity or whatever using electric means, that would be super, because then we can control it technologically. If it's related to radioactivity, so how do I change radioactivity? So it must be something that I can control. So I can have a mechanical approach, maybe a materials approach, or in this case, I choose the electric approach just to entertain you. Yeah? So. Okay, how did I do that? Did I do that? If I look to do propulsion, then basically I need to measure forces. Yeah? So I try to develop the very best thrust balance in the world. Yeah? I try to measure extremely tiny forces, and not only to measure tiny forces, but because I told you I need to somehow do something with electricity, I need to play with this balance with electricity. Yeah? And this is something that doesn't exist. Yeah? So if you buy a balance, let's say from Sartorius or whatever, so typical balance manufacturer, they write in a manual, don't do anything electric with this balance. Be aware that don't charge up anything, this will lead to false measurements. Yeah? Don't connect any cables, these cables will lead to false readings and whatever. So this kind of tool to play with electricity and to look for any connection to gravity or forces doesn't exist so far. So maybe this is the reason why we haven't stumbled across the way how to build a warp drive, because we haven't opened this experimental window up to now. So I tried to build these super balances, and just maybe to tell you how good this balance is a factor of 1,000 times better than anyone else. So we can measure something like 100 piconewton of force for experiments that weigh up to a few kilograms that you can put on this balance. You can heat things up, you can rotate and move stuff, you can apply high voltage, high frequencies or whatever. So the first time you can play with something and measure forces, torques, and changes in weight or changes in mass. So this is the special thing that we try to do here. So this is really unique to check for any kind of interaction that we've missed maybe so far between electromagnetism and gravity. And all that, of course, is in a big vacuum chamber, completely isolated. And you spend years in doing all this isolation, chasing the small little effects. Every couple of weeks, we have a Nobel Prize candidate, and I'm now already so, well, we have seen so many of them that we have a whole list that by 95% I can directly rule it out because of this and that and so on. But it's always fun, especially young students get very excited. They think, oh my God, we found it, and relax. 2 weeks, and I swear we will kill it off our list. But nevertheless, you have to check, yeah? So that's the important thing you have to check. So I have now this new facility for breakthrough propulsion, and we try to put this to the test. And there was a book that I forgot to mention in my dark energy, dark matter slide before. I really like this book. It says, "We have no idea." Yeah? Written by two physicists, and they write about 10 problems in physics that we're aware of. There are a couple of theories about them. Some people have their opinion about it. But if we get to the bottom of it, let's just say we have no idea. We just don't know. Yeah? And they also say in this book, if you have no clue what it actually is, the best way to find something new is to do it very systematically. So make a table of all possible combinations that you wanna, that you think that could be possible, and then, because you don't have a best first pick, you just go through your list and try to check everything. Just don't miss anything. I feel myself like, going back in time to the times of Michael Faraday. Michael Faraday had this intuition there could be a connection between light and electromagnetism, but he didn't know what it was. He tried for years all different combinations until he found out that the magnetic field is changing, it's rotating the plane of polarization of light, the Faraday rotation effect. So actually I have to do the same thing. So I have to say, okay, well, that's what I'm interested in. I want to produce a force, maybe some change in mass or whatever, and on the other side, it's electromagnetism, as we know it from Maxwell. And, let's keep our list as open as possible. Maybe Maxwell even missed something, so, but let's the question mark. Yeah? So we have to make this list as complete as possible. And then we have to ask some very fundamental questions. If I charge up a capacitor, does this capacitor actually, this electric field, does it produce a force? This is a very simple question to ask. Also, for example, if you charge up a capacitor, does it change its weight? You can say, oh, EMC square, sure. If I charge up a capacitor, it will change its weight, but it's so small that you will never measure anything. Then my question is, have you ever checked? Up to my paper that I published this year, no one ever checked this. So I tried to put the error bars on all these different points here. Yeah? So it's an interesting question to ask. Yeah? So is there any kind of fundamental interaction that we have missed? Because actually we haven't measured it so far. Same like a coil. You energize a coil. Maybe does it produce a torque by itself? Does it maybe change its mass? No one has ever checked. Is there a relation between charge and mass? A much more fundamental relation. There are some 5-dimensional theories that predict that. Maybe does a current or a special type of currents, I will come back to that, relate to maybe some kind of force that we're not aware of. So I try to make this very fundamental and trying not to miss anything. Yeah? And do this in a very credible way, build the best measurement equipment, and then trying to answer all these fundamental questions. And I just pick one little slide, sorry, one equation, okay? It's not so heavy, because it's actually really interesting to realize that. It's actually very simple. You can actually, if you just take the square root of the gravitational constant, electric constant, you can, with the units, convert between force and an applied electric field over some mass. It's very simple. Yeah? So the thing is, this coupling constant here is very small. It's so small that actually only my latest facility is able to resolve that. Yeah? But it's possible. Same is, for example, if you have a toroidal coil, you energize it. Also, there's a very simple way to say that, okay, if I have the magnetic field, it has some mass, it could produce a force just from the unit's point of view. There's a guy who claims to have a theory about this. And so actually this toroidal coil could actually make a torque. Yeah? Also, very small coupling constant. It's not something obvious that you have missed in your laboratory. It's very small to measure this. And so let's go to our very first example. It's actually a fascinating story that started something like 100 years ago. In 1927, a guy called Thomas Townsend Brown made a patent and wrote an article, How I Control Gravity. He observed that when you have an evacuated tube and kind of you plate with X-ray tubes, and you energize this tube, so you have kind of a capacitor with plus and negative charges, that this capacity actually starts to move. So something like what I just told you before. You charge up a capacitor, does it produce a force? This guy 100 years ago, he made a patent about this, and he was convinced that this is kind of an electrogravitational effect. This is the myth. If you check on the internet, there are people still right now, even there are patents from NASA and whatever, claiming that this is the case, okay? So this guy was convinced and spent all his life trying to chase this. Thanks, Benna. And he built kind of discs like this, saying that if you energize them correctly, you have this asymmetrical capacitor. This works even best. So if you have a plate and you have a wire and you charge it up, this whole capacitor is starting to move. Yeah? Obviously, he did this in air, by the way. So this is something that maybe I should note. And you can do this kind of in your lab too. So I have this here, for example. You energize this, and you have here a very thin wire. You have here a plate. You apply high voltage. It starts to move. When I show this to my students, same as I was as a kid when I saw this, I said, "My God, what the hell is this? Yeah, this looks like super propulsion, yeah? It's not obvious that there's a propellant flow or something like this. I just put electricity and it starts to move, yeah? So a very fascinating thing, and so I spent quite some time in having a look on that. And so basically in the 1990s, there was already a guy, was contracted from the US Air Force, and they checked this and they said, well, if they put this in a vacuum chamber, this thrust actually scales with the ambient pressure. So when it goes down, the pressure, the force also kind of goes down. So it must be connected actually to air. And in fact, what I did then is to show if there's any kind of anomalous force behind it. I put this all in a completely sealed box, and I checked when I turn it on if the whole box would start to move. So if there's maybe some current flow in the air, that's okay. But if it's really kind of an anomalous force, then the whole box actually should move. So I did this really as a kid, yeah, and as a student. And this is the most highly cited paper, actually, if you check on what's the myth about the Beefel-Brown effect. Unfortunately, I found out it's just an electric wind phenomena, and the force is, my resolution was kind of 10 micronewtons. Within that limit, there is no anomalous force connected with this. Of course, now I'm much, much better than what I was when I was a teenager, and I'm still chasing the same things. Bill is, of course, much, much better. And the latest thing is, we built this in a glass bottle, this Beefel-Brown effect. And trust me on this, to play with these high voltages on that setup, you can see all kind of different forces if you don't really properly shield it. And unfortunately, even down to, well, nanonewton resolution. Sorry, Mr. Brown, but yeah, asymmetrical capacitors so far, in the DC case, do not produce any anomalous force. The second example, maybe, that I would like to entertain you with, just very briefly, is to make you aware of something that maybe we are all not really aware of. We're living here in space-time. Space-time has a very unique, very interesting property. Space-time is everywhere the same. That's an interesting property. It doesn't matter if I'm here or if I'm over here. Space-time is always the same. What does this mean? Do I see this somewhere else? In fact, I do. For superconductivity, you're all aware of this superconductivity. In superconductivity, you also say that basically you create a tabletop atom. You cannot really distinguish where you are, and so you have a loss of locality, and so you see the same things. Yeah. So what if space-time is actually something like a superfluid? if I have a supercurrent, can I interact with space-time in a different way than with a normal current from my coil in a normal, whatever electrical setup that I have? So this is the question I was asking. So I built a setup where I have a kind of a copper rod in the middle, and then I have a superconducting rod on the outside, and I have a current flowing to the left, and then a supercurrent going through the right. And I put this on my thrust balance, in a bath of liquid nitrogen. So this is already something. I mean, this is also the first thrust balance where you can actually work with superconductors. This is also another novelty. And so I tried to check if this arrangement, because the net currents are zero, but in one direction I have a superconductor, another one a normal current, if this is doing anything with space-time. And you can already imagine what's the result, because otherwise I would not be standing here. The result, unfortunately, is zero. Yeah. By the way, the liquid was too much of shaking around, so we had to pump on the liquid to make it actually a kind of a solid. So solid nitrogen was then cooling the superconductor. Super experiment. I love this. Yeah. But unfortunately, zero. Nevertheless, you don't have to give up. You just have to follow this table, and I always look at this table thinking if I'm missing anything here. Yeah? So that's the thing. Just have to keep going. I'm convinced, maybe, I mean, this is kind of the vision, if there is any kind of connection here. Check out my latest paper in Scientific Reports. I published 4 years of conclusion of what I did in the DC case to check this table, if there's any kind of connection there. So that was really fascinating. So I believe we will make it happen eventually, because, I'm free to believe whatever, right? I'm free to choose whatever I believe. So I believe we will make this happen. And the important thing is there is no plan A, but nevertheless, you have to keep going. You have to do very credible science, and you have to go beyond our present boundaries to make it come true. And, as a good engineer, also first lesson in my class is you always have a plan B, right? You always have a plan B. Yeah, if someone is asking you if it's possible, you always say yes. Yeah, it's just a matter of time and money, and if I cannot achieve this, then I have a plan B. What is the plan B? We said we can do 2 of these 3 limits we can do. Just one I have to get rid of. I need to get to the next star. Cannot change that, yeah? And I want to go there with something. So there's only time. I have to eliminate time. So yes, sure. Actually, it's possible to eliminate time, because who says that it's us going there, right? Who says that GPT-10 is not at least as intelligent, or probably even more, than we are? So maybe we're just a couple of years away, and they don't care if it's a 10 or 18,000 years journey. We will launch an interstellar spacecraft for sure within our lifetime. Yeah? Maybe we will not be around, but someone or something will be around to do it. Okay? So that's a good thing. We will do it for sure. But of course, I'm also a sportsman, yeah, and I see the little competition. So it's either them or us. So who will be first? This is the challenge here, yeah. They will maybe take 18,000 years. Maybe I can do it in 50 years. Thank you very much. Yeah.